Water is the lifeblood of our environment. It's literally our lifeblood as well. We've been relatively secure in New England and in Vermont forever, that we don't really need to worry about water. We have plenty of it, and it's in very good condition. Increasingly, that water may be contaminated for uses that we want to put it to.
In the coming century, water will be the critical resource that we'll be concerned about. How much we have, how clean it is, and is it distributed in time and space in a way that will sustain human and other biological populations.
Emerging Science is a Vermont Public Television production in partnership with and funded by Vermont NSF EPSCoR. EPSCoR, supporting science and engineering in Vermont colleges and businesses and encouraging young Vermonters to seek careers in science.
Water makes life on Earth possible. Our planet maintains a delicate balance of air, sunlight, and water, and serves as a most gracious host to a phenomenal diversity of plants and animals. Throughout Vermont history, we've enjoyed more than sufficient water reserves. However, development patterns, the extraction of natural resources, and the emission from our industrial society jeopardizes the quality of our water. Currently, water is abundant in Vermont, but around the world, we increasingly hear reports of drought, water scarcity, and even water wars. However, scientists are working to understand and solve these crises. I'm Amy Seidel. Welcome to Emerging Science. Scientists realize that the Earth is one large closed system, meaning we have to consider the entire planet when making decisions affecting our natural resources. To model our natural systems, we start with a smaller scale point of delineation. For water researchers, this point is the watershed. Here in Vermont, this includes the Champlain Valley watershed.
Lake Champlain is a really unique lake. There's 19 times as much land area as there is water area in the whole Lake Champlain basin. When it rains, 19 times as much rain is falling on the surrounding landscape as is falling directly into the lake. The lake is the accumulation of everything that we do on the landscape.
If you look at the watershed, you're looking at how the water connects everybody in the watershed up. If somebody does something to the watershed, other people downstream are gonna brunt the effect of that. So if you change something in your forest or you change something in your agricultural field, we as a community who are sharing the watershed together will all feel the brunt of it, so we all have to share that responsibility.
The Champlain Valley watershed is an intricate network of streams and rivers, with Lake Champlain receiving the runoff from the lands between the peaks of the Adirondacks and the Green Mountains. Let's take a look at the geological forces that created this beautiful valley.
With the work of hundreds of scientists over dozens of years, the story's been pretty well pieced together of the landscape history of New England as a whole and Vermont in particular. We can talk to people, we can look at news reports, and we can understand what's happened in the last decade or perhaps even the last century. We can use photography to take us back now more than 150 years in Vermont history. We can use diaries to go back perhaps a couple centuries. But to go beyond that requires the tools of a geologist to look back and interpret what's been left behind in the record here. In relationship to water, the geology of the Champlain Valley is a combination of understanding the bedrock here that underlies the valley and the glacial sediments that lie on top of it.
The bedrock formations on this side of the valley in the Green Mountains, and then from the Green Mountains down to the valley, you have extremely old bedrock. I believe it's like 1.3 billion years old.
Glaciers probably started moving across Vermont, continental glaciers, ice sheets from Canada 2 million years ago. And they may have moved across Vermont dozens of times, but each advance wiped out the evidence of the one beforehand. The last advance ice covered even the highest peaks in our state with ice, and the terminus of that ice was down in New Jersey and Pennsylvania, and Long Island, Cape Cod.
When you look at a glacier in a cross-section, The bottom 30 to 50 meters of ice can be as rich as like 95% of sediment that's being carried along. As the glaciers move forward, that's when it's doing the scouring, the plucking, picking, whatever you want to call it. Probably, it's estimated at least a mile of rock was removed just with the last glaciation. As the glaciers recede, it's what's left behind that's determining what you see.
The sediments that were deposited when the last ice sheet melted away 12 to 15,000 years ago are really in many places the prime aquifers, the places where we get a lot of water out for use.
The formation of the soils that we see, or just in general all the sediments, are a consequence of the melting that took place probably at catastrophic scales when the glaciers retreated. There was about a mile of ice at this latitude. Because these glaciers have all extended, they've cracked open, there are crevasses, the water is running down into the bottom, making their way all the way to the bottom through a network of cracks. And this water can just be building up on the bottom, and then all of a sudden there's a burst. A pathway is found, and you get this sort of catastrophic outbreaks of water. And you can get just tremendous buildup of sediments. If you were to have been here maybe 9 to 12,000 years ago, there'd be a gigantic chunk of ice here and a gigantic chunk there. And finally, when those chunks melt out, oh, there's a lake left by. Some of these tills are so tightly compacted that they don't pass the perk test, as they say around here. It takes a long time for water to drain through. And the reason is because you have these boulders surrounded by gravel, and then the little holes around, which we call interstices, are filled by sand, and the holes in the sand are filled by silt, and the holes in the silt are filled by clay, and it has very, very low porosity.
The incredible forces of the last ice age carved out the Champlain Valley and left behind the topographic features that orchestrates the way water flows. Even in modern times, natural forces continue to sculpt our landscape.
Since the glaciers left, Vermont's been affected by a number of what we would term forcings. One of these are large storms or hydrologic events. And so most days not much happens. The river flows are about average. The snowpack sits there and melts slowly. But occasionally, once, twice, 10 times a year, something bigger happens. We get a big storm. We get a big thunderstorm, we have a very rapid snowmelt. It's those events that move a large amount of material and can really help shape the landscape. The 1927 flood is the flood of record in Vermont. It's the flood that the old-timers still talk about. It's the flood that books are written about. Between 1,000 and 1,200 bridges in Vermont were destroyed by that flood. It really shaped not only the consciousness of many Vermonters, but the landscape, the river channels. Many people would say that flood is unusual. It's a really rare event. But by looking back at the geology, one can tell that that kind of 27 flood probably shows up on the order of once every century or two. And it may not affect the entire state at that time. Floods like that affect parts of the state. And I think that puts our human perspective of these major events it gives us sort of a reality check that we will see these kinds of floods again. We've seen them in the past, and the geology tells us we've seen them many times in the past.
The flood of 1927 and annual spring melts in Vermont remind us that too much water can be a problem. But a growing concern around the world, and in Vermont too, is just the opposite. That is, the availability of clean water. To explore this crucial issue, we need to understand the hydrological cycle, how water moves and where it is stored across the landscape.
Water cycle basically is just what it says. It's a continually circulating water body. It can start in clouds, reaches the Earth's surface. Some goes over the Earth's surface, some goes into the Earth's surface. That goes into the Earth's surface eventually makes its way through the ground and reappears on a surface water body like a lake or a stream. That goes to perhaps the ocean where it evaporates, goes back up into clouds, and you go through this whole cycle again. An aquifer basically is soil that contains water that can be withdrawn through wells at a rate adequate to provide a groundwater supply or water supply to a home or to a business or to a municipality. So it's basically soil formation capable of yielding reasonable amounts of water to wells. In this box we have a very large number of sensing devices. And it's filled very carefully with soil so that it can mimic what we see in the field. There are 105 locations in the box where we have these devices, and each device essentially contains several different measurement instruments. One for temperature, one for pressure, one for concentration, and so on. Now we have a system we can control, and we can now compare our math models against what we see in this intermediate scale facility to give us confidence that we have all of the mathematics correct. And then we can take those mathematics with the computer, go into the field, and solve real-world problems. So this was designed essentially for that purpose. And more specifically, we were interested in looking at the issues of contamination, how they move through the soil, how they change as they move from one side of the box to the other. So we wanted to capture all these different physics that you might see in the real world.
At the moment, Vermont appears secure in its supply of clean water. Some in Vermont have elected to participate in the $11 billion per year bottled water industry. The ownership of Vermont's drinking water is being debated in state government. From an ecological standpoint, maintaining abundant clean water means maintaining the health of natural ecosystems, particularly wetlands.
We have an amazing collection of water resources and water systems in the Lake Champlain Basin. We see the lake in the middle, we see the rivers that connect to the lake, but those rivers are actually fed by groundwater reservoirs that are often recharged by associated wetlands. We have an amazing number and diversity of wetlands in the Lake Champlain Basin, and the wetlands store water during wet periods of the year, and that water actually percolates down through the soil into the groundwater, and then the groundwater flows and maintains the small tributary streams, which then feed the bigger streams and head down to the lake.
Wetlands are critically important components in the biosphere. They are filters for nutrients and pollutants. They're critically important habitats for a number of rare and endangered species, both plants and animals. They're nurseries for a very large percentage of the fish that we find in both freshwater and marine environments.